Oh, thank you very much for the invitation. So today I'll talk about open-closed Gromov-Witten invariants for Toric Calabi-Yau 3-Orbifolds. This is based on joint work with Bohan, Fang, and Hsian-Hua, Tseng. So let me first, so we will prove some mirror theorem. So first, on the A model, so for the geometry, we have Toric Calabi-Yau 3-Orbifolds. I will describe what they are, and then we will define. So the closed string moduli on the A model, these will become classified Kähler classes, and we will describe Aganagic-Vafa A-branes. These are a special class of Lagrangian submanifolds of Toric Calabi-Yau 3-Orbifolds. And so for the B model, we will have the geometry of mirror curve, and the Aganagic-Vafa B-branes, like very simple complex cycles. And then we will define open-closed Gromov-Witten invariants for Toric Calabi-Yau 3-folds relative to this Lagrangian brace of Aganagic-Vafa types. And finally, we will state a mirror theorem for the disk potential. So let's take a three-dimensional Kähler orbifold. So locally, it is given by C3 mod by a finite group, and the group action preserve the symplectic structure omega and the complex structure J. So we say it is toric if it contains the three-dimensional algebraic complex torus as a dense open subset, and the torus action on itself extends to a holomorphic T action on X. And if you restrict the action to the X maxima compact subgroup, which is U1 to the third power, then it's a Hamiltonian action on the symplectic manifold. So, so that's a toric 3-orbifolds. And we say this toric 3-orbifold is Calabi-Yau if the top exterior power is an honest bundle, not just an orbibundle, and it's trivial. So the coarse moduli space of such is actually a simplicial toric variety, and it can be defined by a simplicial fan in R3. So a simplicial fan consists of some simplicial cones. So let me give you some example. So for example, if you do so if you do C3, so actually by the Calabi-Yau, so we will have a fan in R3. So we will have like the set of one-dimensional cones, and so for each one-dimensional cone, we can take so this is generated by some integral vector, and so because of the Calabi-Yau condition, so we can actually may assume that each VI it's a vector in these three, and we can assume that the last component is actually 1. Yeah, so let me take the simple example. This is just the most simple, like toric Calabi-Yau 3 manifold. So C3, so we can take so we only need to look at the first two components. So V1 is 1, 0, 0. V2 is 0, 1, V1 is 1, 0, 1, V2 is 0, 1, 1, and V3 is 0, 0, 1. And then using this so we get so this matrix gives a map from C star 3 to C star 3. So it's given by T1, T2, T3 to yeah, so this kernel is, so the kernel is trivial. So then, in this case, our Toric Calabi-Yau 3-fold is just given by C3 mod by the trivial group. This is C3. So let me give you a non-trivial example, which is actually an orbifold. So example 2. So suppose that we take another, so take so if you take the, so in this case, so if you take the cone over it, you get a simplicial cone spanned by the following 3 vectors. So 1, 0, 1, 0, 1, 1. And then so now we take the toric variety associated to this single cone. It has 3 one-dimensional cones and 2 two-dimensional cones. So you should think this is the cross-section of this cone on the plane Z is equal to 1. And then you consider the, so this defines for you T1, T2, T3. So you just read this and you see that this is so this phi has a kernel. So the kernel of phi is actually so it's actually generated by, so it's actually 1, 1, 1, omega, 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 and omega square, omega square, omega square, where omega is a third root of unity. And then you take your toric varieties defined by C3 mod G, which is C3 mod Z3. So for the orbifold, we just take like the orbifold quotient of this. Yeah, so you see if you have a simplicial cone, so this defines, this simplicial cone defines a smooth, defines a C3 or a smooth affine toric variety of dimension 3 if this 3 vector form an integral basis. Yeah, and it forms an integral basis if and only if this triangle has area 1/2. So in general, it will only be a rational basis, and it generates a sublattice of finite index, and that index is equal to the determinant formed by these 3 vectors, and that determinant is twice the triangle. So that triangle has area 3/2, so you get a finite group of order 3. Okay, so now we can, so if we want to so then we can actually subdivide this. So this is simplicial cone. So now we get another Fang. So now it has 3-dimensional cones. So we add V4. Oh, so this is 0, 0. So V1 is 1, 0, 1. V2 is 0, 1, 1. V3 is -1, -1, and we add V4, which is 0, 0, 1. So then this toric variety will be, so we have 4 vector, it will be C4 mod some group. So then this group will be the kernel of this group homomorphism from C star 4, because we have 4 vectors to C star 3. So, and this map is given by, so you can so we see that the kernel is actually C, and this map is given by T, T, T. Oh, so it's actually, we need to take out some bad locus. Yeah, so in general, so from these vectors, so you already know this C4, this 4 is equal to the number of 1-dimensional cones, and you can know the group and the group action just from these vectors. And then you look at the actual cone, and you know you need to take away some locus. So in this example, you know like x is actually equal to so where C star acts in this way. So in general, for any Toric Calabi-Yau 3-fold can be written in this way, and you can actually just read off all the data you need from like this. So from a picture like this, you have a collection of triangles. So each triangle corresponds to a top-dimensional cone, and that triangle corresponds to a C3 chart if and only if the area of the triangle is 1/2. So any questions? So these are Toric Calabi-Yau 3-Orbifolds. Okay, and then yeah, so there are general construction of like smooth toric Deligne-Mumford stack in terms of stack key Fang due to Borisov-Chen-Smith. But since we are looking at very special case, Toric Calabi-Yau 3-Orbifolds, so they are given by these pictures. So, and moreover, since we are assuming it is scalar, so actually yeah, so the union of this triangle will always form a convex set in the plane. Oh, so since now X is presented, so the toric orbifold is presented as the quotient of some dense open subset of C R prime, where R prime is the number of one-dimensional cone quotient by G prime, where G prime is a subgroup of C star R prime. And R prime is equal to the dimension of G prime plus 3. So for such a quotient, and moreover, this G prime is a abelian group. So I will define the notion of inertia stack just for this particular case. It's a global quotient by a abelian group. So it's actually a disconnected union. So for each, yeah, so you look at the, yeah, so there will be finite. So because so the stabilizer for each point is finite. So actually this will be a finite union. And then UK means the fixed locus of K. So for most K, there will be like no fixed locus. So then, so the orbifold cohomology is defined by, so you take the cohomology of an initial stack, but for the case component, so you actually shift the degree. So let me tell you how we shift the degree. So you look at the, so you look at K in G prime, so fix, so then you look at some point X in the inertia stack associated to K, and then K fix it. So K acts on the tangent space, and by so, and these are not unique, but if you restrict yourself, if you require that epsilon 1, epsilon 2, epsilon 3 is greater or equal to 0 and less than 1, then these numbers are actually unique. And so the age of K is defined. It turns out that it will be independent of choice of your point. So this is. So in general, this can be a fraction number, but because of the Calabi-Yau condition, we know if we take the product of this should be like 1. So because of the Calabi-Yau condition, this can be 0, 1, or 2. Okay, so that's the age. So for example, okay, let's take this example. So that so then the inertia stack is actually the union of x1, disjoint xg, and xg squared. So g cubic is the identity. So then if you look at the, so the action of, so the action of the identity on the tangent bundle is trivial. Oh, so x1 is just C3 mod Z3, and then for xg, is actually just the only fixed point of G is, so it's the classifying space of Z3. And if you look at the G action at the on the tangent space of the origin, you see that the weight is just this. So the so Hg is 1/3 plus 1/3 plus 1/3 is, which is 1. And so it is also BZ3, and Hg squared is 2/3 plus 2/3 plus 2/3, which is 2. So in this example, we see that the orbifold cohomology, we do rational coefficient. So of C3 mod Z3 with this action. So this is so where degree of 1 is 0, degree of 1g is 2, and degree of 1g squared is 4. So it has H0, H2, and H4. Okay. So these are, so any questions? Okay, so that's the Chern-1 orbifold cohomology defined in this particular setting. So next, okay, so the A-model closed string moduli is complexified Kähler classes. So actually, any such Toric Calabi-Yau 3-Orbifold can be written as a symplectic quotient. So we can actually, there exists CR. So because you see in the example of C3 mod Z3 is C3 quotient by a finite group. But actually, if we increase the dimension of C3, it's possible to make it as a quotient of a connected torus. So it is always possible to write it as a symplectic reduction of like CR with the standard symplectic form mod out by a connected torus. And then, so this, so the moment map is determined by the action of U1K on CR. And we call these integers charge vectors. So, and then this X is the geometric quotient, actually the GIT quotient of a CSR action by the complex torus G, and it's also the symplectic quotient of the compact torus GR. And X is the geometric quotient or GIT quotient, and our orbifold is just the stack key quotient. Yeah, so then this R1 to Rk, so if you choose different, so the image of the moment map is Rk, so if you choose different valued, you will get different Kähler class. Also, there are also chambers. So then we call like this, so we have some complexified Kähler parameters. such that the negative, the real part is just this real Kähler parameters. So this will be like these parameters will come up later in our definition of generating functions. So for example, if you consider the U1 action with charge vector 1, 1, 1, minus 3, so you can see that the moment map is given by this. When R is greater than 0, you get the total space of O minus 3 over P2. But when R is less than 0, you get this orbifold C3 mod Z3. So in general, how to choose this additional vector, right? For example, you have C3 mod Z3. Yeah, since it's three-dimensional, actually it's always, so you just take all the lattice points. So in this case, there's one lattice point. You add a lattice point and you subdivide it. And then you can, so you know that, so this will be, because this will define a smooth toric threefold, so it can be written as a GIT quotient by a connected torus. And if you go to another chamber, you can get the GIT quotient. So you can present your orbifold as a GIT quotient by a connected torus. Oh, so our Aganagic-Vafa brane, yeah, so it's probably hard to like, so basically for the Aganagic-Vafa brane, so it can be defined, so yeah, so on the, so before we quotient by the compact torus, so these are defined by fixing the, yeah, so defined by like 3 extra conditions, which will cut down the dimension by 3. So after quotient, you get something three-dimensional. So this was first introduced by Aganagic-Vafa for smooth Toric Calabi-Yau threefold. But we can also define it for Toric Calabi-Yau orbifolds. It's just like it is so if it's a smooth Toric Calabi-Yau threefold, then this brane is always, yeah, I can give you one example. So for example, for C3, so yeah, it always looks like this. First, such a brane will be contained in a, like in the smooth case, it will be contained in a C3 chart. So you should view this as like, you know, the moment polytope of C3 looks like this, and you're projecting it down. And then this, the image of this Aganagic-Vafa brane, so in the moment polytope will just be a ray starting from here, but it will be like in this direction. So the image under the moment map is a ray whose endpoint ends on an edge, and yeah, so the other points are in the interior of this polytope, and actually polyhedra. And then if you look at, so you know that if you take any point in the interior of this polyhedra, and the pre-image is a 3 torus. So, but the fiber is a 2 torus, and this 2 torus shrink to a 1 torus. So the topological type, so in the smooth case, so this Aganagic-Vafa brane is always of the type circle times R2. So now in the orbifold case, where is the, and then it will always, so if we look at the, like if we draw in the smooth case, So you see, so this is the image of the moment map. So this is a ray, but the pre-image is a T-fixed copy of C. And we have, in this case, if this is C3, then these are the 3 axes. And your brain looks like this. So in the orbifold case, it's just this picture will be replaced by C3 mod of finite group G. And this L will be, yeah, actually, if we look, we can look at in a chart. So this X sigma is, in general, a chart on a Toric Calabi-Yau 3-Orbifold is C3 mod of finite group sigma. Yeah, so then the action of this so this G sigma is the stabilizer of the origin. So the action is given by some characters. So G sigma, so it has 3 characters, corresponds to the action on the 3 coordinates. And because of the Calabi-Yau condition, so if you take the product chi1, chi2, chi3, you get a trivial character. And the kernel Ki will be the generic stabilizer on the ice axis, right? So the character the character will generate a finite cyclic subgroup in U1, which is like mu Si. So it's Z mod Siz. So, and then there is a G sigma equivalent diffeomorphism L tilde sigma from L tilde sigma to circle times C. So the action of this finite group is given by this, right? So then your Aganagic-Vafa A-brane is always looks like this circle times C quotient by this action of G sigma by an action like this. So if, of course, in the smooth case, this is trivial action, so it's circle times C. So in general, you see that this is homotopic to, so we want to understand the first homology of this Lagrangian actually suborbifold. So in general, you will have some generic stabilizer along this circle, right? So actually, that's the generic stabilizer along the circle is this. So for any point on circle times 0, the stabilizer is K1, right? So then it's a K1 banded germ over S1, and you can check that the first homology is given by a pair G D0, where D0 is an integer, and that's actually corresponds to the H1 of the coarse moduli space, which is homotopic to an actual circle. So it can be identified with this subset of G sigma cross Z, such that chi1G is equal to that. Any questions? Yeah, so these are all very, simple. So so this will be our Lagrangian boundary conditions in our setting. Okay, this is, so also there is a, there is a framing. So there's a, so because of the Toric Calabi-Yau condition, so there will be a, So then there will be subtorus T prime so this X on the canonical line bundle. And then this has so the choice for each given at PT sigma so this T prime axon so you choose a choice of framing is just a choice of a subgroup of these two torus, one-dimensional subgroup of these two torus. So it's determined by like the slope, which is Okay, so now these are the geometry on the A side. So now let me tell you the geometry on the mirror side. So we will have, first we will construct the mirror of this Toric Calabi-Yau 3-Orbifolds. It will be a non-compact hypersurface in C4. Actually, so we consider, so recall that, so this R is, so first we present our Toric Calabi-Yau 3-Orbifold as a GIT quotient of C to the R's power by C star R minus 3. And then we consider the following equations. So first we look at so our Lagrangian is in some contained in some chart, and then so each of these faces correspond to a divisor, and each divisor corresponds to a one-dimensional cone. So suppose that this is DI1, DI2, DI3. So before you do the quotient, this corresponds to the coordinate so this reduced to DI in R. So that's how you choose. So these are, so we have, these coordinates xi's are in one-to-one correspondence with one-dimensional cones, which are in one-to-one correspondence with this T invariant divisors. So we look at where our Lagrangian is, and then we choose 3 of them. So if L is here, so I1, I2, I3 are these 3. So then so this is just some recipe, but it will work. So you choose so you let xi1 to be this, so xy will be coordinate on, xy will be in C star. So then for this, so here, this, and then you have k equations. So these are given by the charge vector. So you have k of them. R minus k is equal to 3. So now with all this equation, this will completely determine all the xi's in terms of little x and little y. Okay, so just solve it. We will do an example. For example, so we will do one example later. But then these equations, so then we plug in here. So then we will get the equation in terms of little x, little y, and this QAs. So the mirror Calabi-Yau 3-fold is given by the following. So it's a hypersurface in C2 cross C star 2 given by this equation, and it's parameterized by this Q. So you see the number of Q's are the same as the number of complexified Kähler parameters of our original Toric Calabi-Yau 3-Orbifold. And so you see this, so we have this Q1 to Qk. They are the complex moduli of this family, this mirror family of non-compact Calabi-Yau 3-fold. And yeah, so now we can so the frame mirror curve can actually be identified with the moduli of Aganagic-Vafa A-branes or B-branes. So because if we look at the, so for example, if we have O minus, so then you actually will get the picture. So we have this picture, but if you look at, so these are the, if you take the cone, you get the cone over this picture, you get the fan defining this. But if you look at the dual picture, so moment polytope, you actually get this. So this is the, yeah, so actually this, so this is the base P2. And these are the other three T invariant divisors. Yeah, so you know that what is the moduli of your Aganagic-Vafa A-branes, because you can actually move it along here. But then we also complexify that. So after you complexify it, so the moduli actually looks like this. But this is actually, so you see if we do the recipe of the previous page, so because recall that for C3 mod Z3, so this is given by, so the action is given by 1, 1, 1 minus 3. So if we take the recipe in the previous page, and if we get, if this is our, if our Lagrangian is actually yeah, so actually let me do a C3 mod Z3. Yeah, so this is D4, D2, D1, D3. So if you apply this to D4D, so you actually get this equation. Yeah, so you can check actually this is a fine curve in C star 2, and it looks like this. It's like genus 1 with 3 punctures. Yeah, so in general, depending on where, so if you do C3 mod Z3, so C3 mod Z3, if obtained by you blow, so yeah, so you actually just have this, because if you blow up the 0, 0, 0, you get that picture. So if you put your Lagrangian brane here and you use the recipe, this is the equation of the mirror curve you get. So in any case, in general, once we have the Toric variety, and I tell you the Lagrangian brane and the framing, then we can write down this mirror curve explicitly. So it's an affine curve in C star 2. Yes. Yeah, so of course there's some like so roughly, at least for some, maybe not for the whole curve, but for most of the curve. So this is yeah, so basically, so this, the moduli is, so it's like the, so yeah, if we look at the, think about, so basically the moduli, the open parameter is like the complexified area of this disk, right? Yeah, it's like, yeah, it's like this. This is, so L looks like this. Yeah, in this case, actually the action is free on this Lagrangian. So in this C3 mod Z3 case, it actually looks like this.
But I wondered what happens when that circle goes down to the point.
Oh yeah, so then you have some. Yeah, so then you have some. So then you will have like you have some wall crossing. Yes. So yeah, so there's a recipe to write down this mirror curve. And now I'm going to tell you like the, yeah, so the topological open string in the A model. So if we have a Aganagic-Vafa A-brane, that which I defined above in a Toric Calabi-Yau 3-fold, so the like open Gromov-Witten invariants of this pair should count holomorphic maps from an border Riemann surface with orbifold points, possibly with orbifold point in X with boundary in L. Yeah, and then, so what are the topological type of such map? So first, it is given by the topological type GH of the coarse moduli of the domain. At least when the domain sigma is smooth, it's a border surface with G handles and H holes. And also, we also have like the degree of the map, which is a push forward of the fundamental class of the domain sigma. It's a second relative homology class. And now, as we said, we also have these boundary circles. So each of these should correspond to, we can specify their class in H1 of this curly L. And as we said, so H1 of curly L can be identified with a subset of this. Yes. So, and finally, we also have this framing. So when you have all this topological data, you can form a moduli space which parameterize this map. You need to compactify it. You need to allow like nodes, and you can have orbifold points. Like the nodes can have orbifold structure. But in any case, there is a moduli space, but this moduli space like has corners. So we actually like, so given such moduli space, so the domain has topological type GH, and we have M like possibly orbifold point, and we have evaluation map at this orbifold point, but now the evaluation map will take place in the inertia stack. So we can pull back cohomology class from the inertia stack. So, but we will use the orbifold grading. And then we actually define this by localization using the, so we have this F, which is tells us some one-dimensional torus. So we use that one-dimensional torus to define this invariant by localization. So it's some equivariant invariants, not. So it will actually depend. It will depend on F, the framing. So yes. So now we can form a like. So if we, it turns out that if we pull back, because of the Calabi-Yau condition, if we pull back classes in H2, then we will just get some character. So we will just get a number depending on F. And then we can form a generating function. So now we fix the topological type G actual domain. We sum over this windings monodromy, windings mu J, monodromy Kj, and the degrees. So yeah, actually this, yeah, so this degree is hidden in this tau, and oh, so this is the general definition, but now it will not be like, it will has value in the tensor product of H copies of P sigma. So P sigma is this stacky point. Yeah, so these are the generating functions. So this is how we define it. So now, yeah, lastly, I'll just be able to state the mirror theorem in this case. So if we take the like generating function of this orbit disk invariant, it will takes value in the oh, sorry, I should say orbifold cohomology. So if this P sigma is actually has stabilizer G sigma, so this is yeah, so it will take value in here. So now we want to define some complex valued function. So the complex value function is given by the following. So we define a character which depending on this F from G sigma to U1. So we take this coefficients, so each coefficient will be a rational number depending on F. But now if we form this, it will be, the coefficients will, we have this power series, the coefficients will be in general complex. So we need to do this in order to match the B model. So for the B model potential, so recall that, so we need to know the Calabi-Yau 3 code together with the Lagrangian, together with the frame to write down the equation of the mirror curve. But once we write down the mirror curve, we can solve y like implicit. So actually, there's something we need to be careful. So we have this log y, and we need to take certain branch, and we need to expand at certain point. But then if we do it carefully, then we get some, yeah, we get this logarithm part, and then we get the power series in x and all these complex parameters. And we can write down, yeah, actually, so what we can prove is under closed and open-closed mirror map, so this power series is identified with this power series. So there are some explicit change of variables relating capital X and small x and capital and tau and small q. Yeah, so actually the proof is, so we compute it by localization, and then, so for the sum, roughly speaking, so for the sum of degree, we can use the mirror theorem, and then we still need to sum over the windings. And then we get some, actually up to the mirror transform, we get some solutions to the extended Picard-Fuchs equations, and then we can also relate this, like this is actually a path integral. It's like really a path in on a complex affine curve. Yeah, so we can also relate this integral to extend the Picard-Fussy equation. And then when you expand it, the coefficients are in general not like real. So yeah, so in the smooth, so this conjecture was like in the smooth Toric Calabi-Yau 3-fold case was conjectured by Aganagic-Vafa, Aganagic-Vafa like more than 10 years ago, and we proved this smooth case earlier. So maybe, yeah, I'll just finish by showing you some examples. So for example, if you do C3 mod Z3, the open mirror map is the identity. The closed mirror map, so this tau 1 is, yeah, tau 1 is you take, so because in this case, like H2, we can only insert H2 orbit. So H2 orbit is one dimensional. So there's only like one parameter. And it is related to the complex parameter by this closed mirror map. And then you can write down this W explicitly. And with this, then you can know the disk potential. And the other example is like with a different action. So now, so it's still Z3 acts on C3, but the action on the first coordinate is trivial. So it looks like, so the action looks like, yeah, in this example. Yeah, so in this example, so the open mirror map is still trivial. So to get some non-trivial open mirror map, you actually need something which is not affine, but it's more complicated. So the closed mirror map, so if you compute the like orbifold cohomology of this, you see that so this is Q1 plus Q. So now both of this has degree 2. So now you have 2 degree 2 classes which you can insert. So you have two taus, and then on the mirror side you have 2 complex parameters that they are related by this formula. And then the B model disk potential is given by this. So you use this and you can get the A model disk potential. So I'll stop here. Thank you for your attention.